Okay, let's get started. Welcome everyone to the Red Bull Racing Honda Hands-On Lab. My name is Tara Van Cleve and I'm a marketing event manager for the developer initiative here at Oracle. Today we're excited to show you how to use open source machine learning across various Oracle Cloud platforms to prototype predictive algorithms and display outcomes. If you do not currently have an Oracle Cloud account, we encourage you to create one now. We'll be recording today's session, so if you'd like to follow along with the lab walkthrough and then complete the lab later at your own pace, we'll be sending the link to the recording in the next couple of days, and it will also be available on the Modern App Dev series page and Oracle Developer YouTube channel. You'll also have the opportunity to participate in a short quiz on the material covered in today's lab. Upon completing the quiz, you'll receive a Developer Masterclass badge that you can share to your social media, recognizing your commitment and earned expertise. If you have any questions during the lab, please ask them in our Slack channel, which I will place again in the chat in a moment. We'll have several solutions experts and cloud engineers answering your questions throughout the lab there. Today's lab will be presented by Brian McDonald, Master Principal Cloud Architect. So without further ado, I will turn it over to Brian.
Hello, excuse me. Hello, everyone. Yes, my name is Brian McDonald, and I will be kind of leading you through this journey of building some predictive models, leveraging some racing data that we download from the internet. So as many of you may have heard, Oracle has entered into a partnership with Red Bull Racing Honda, and we're doing lots and lots of data science, machine learning, high performance computing to assist them in their efforts to essentially win races. So what we want to do is kind of just walk you through today a little bit about understanding how F1 racing works, how cars and drivers and constructors look at the data for looking at how their teams are performing, as well as looking how you can leverage tools like Jupyter Lab and Python to build out predictive models, and we'll ultimately show you a way to predict the end results. So as Tara mentioned, there's going to be some quizzes and a link to looking at a badge, but to help kind of get people in the mood of using the Slack channel and testing to make sure it works, we'll give out a Source of Pride award. Nothing probably physical, just the pride of anybody who was able to recognize the intro music. It was a remix of an old song. So just for fun, if you get a second, just start to get engaged on Slack and enter the title of the song and the artist. So with that, let's get started. So the first thing that everyone's going to need to do is provision your free tier account. Some people hopefully did this ahead of today's session, but we realize not everybody has the time, or you got your emails just a little while ago and saw it. So we're going to set up some time to do that. So what I'd like to do is first play a little video that walks you through the steps of how to do to sign up. So this is using our free tier. So you'll get credits to do the lab, keep the environment around to play with after time. So don't feel pressured if you just want to listen to me go through this, or you don't complete things within our 2-hour session. So let me start. I'll start the video, listen to it for signing up for anybody who hasn't, and sign up. And then if you have any questions, again, primarily use the Slack. If you have any channels, we'll also be monitoring the Q&A.
Hi, I'm Victor Martin from Oracle Cloud. I'm going to walk you through the steps to sign up for an Oracle Cloud free tier. Please follow along and pause the video when you need it. Oracle Cloud free tier gives you a set of always free cloud services. These services will be available forever. 2 autonomous databases, 2 virtual machines, up to 4 ARM processors virtual machines. You will also have a load balancer, block, object, and archive storage, monitoring, and much more. As part of your Oracle Cloud free tier, you will also have a 30-day trial with free credits to use in other services from analytics to Kubernetes. Sounds good, isn't it? Are you signing up for an upcoming workshop with us? Please make sure that you use the same email you use for the registration, as we have activated a special offer and you won't need your credit card to sign up. In any case, Oracle Cloud is not going to charge you for your trial. You actually have to explicitly tell us so when you are happy with all the Oracle Cloud services after your trial. Let's dive in. You need to add your country, then your first and last name. You also have to provide your email. Oracle Cloud has to check you are a human by asking you to resolve an easy challenge. Finally, click Verify my email to move to the next step. If your email has been activated for the offer, you will see the special Oracle offer pop-up window with the type of offer already selected. Then click Select Offer. All the initial information is already in. Now you have to provide a strong password. I use a generated one, but you can select any you like. Just make sure you are in compliance with the strong password pattern. Confirm the password by typing it again. Fill the company name if apply. The cloud account name is essential as it is a unique identifier for your account. Select a name you like that is not taken. The home region is the region where you are more likely to deploy resources. You can deploy to other regions by subscribing to them. However, your free trial only supports one region. Select a region geographically close to you if you are not sure. I'm selecting Frankfurt region. At the bottom, click Continue. Fill the address information with city, postcode, county, and your phone number. Click Continue. The final step is to accept the agreement and click Start my free trial. Oracle Cloud starts provisioning your account. This takes on average 1 minute or 2. Then you are going to be redirected to the Oracle Cloud web console. Can you see the message "Your account is currently being set up"? It means that some services will still be unavailable for a few more minutes. Just keep it in mind. When Oracle Cloud fully provisions your account, you will receive an email. I will show you that in a few seconds. Go to the menu to explore Oracle Cloud services. Also, the search bar is a friendly tool as you can search for compute instances, Kubernetes engine, analytics services, cost tools, user management, autonomous databases, Apex instances, and much more. On the right side, you will see the region you selected when you sign up. The next icon is Cloud Shell, a small free Linux instance with several tools pre-installed and configured like OCI CLI and languages like Java, Node, Python, and more. You can close Cloud Shell now. Confirm with Exit. The next one is Announcements for updates from Oracle Cloud. The following is the Help icon, where you can find documentation links, chat with us, post questions in our forums, and finally, create a support request and request a limit increase. The next icon is to change the language, and the final one is the Profile icon, where you can see your user information, your tenancy, and the Sign Out button. After a while, the message saying that your account is being set up will disappear. After a few minutes, you will also receive a Getting Started email and another one when your trial account is fully provisioned. Use the button in the email to sign in whenever you want in the future. You are all set up to enjoy your new Oracle Cloud account. Happy hacking!
All right, so everybody should have signed up by now. Maybe some of you are still filling out some of the forms. That's okay. We're going to leave plenty of time for everything to get set up. And again, if you have any issues with the sign-in process, please post in the Slack channel. We have a bunch of people to help me answer questions, resolve any kind of issues you may have. So at this point, you've either created your cloud account and you have a tenancy available for your use, and you have an email with the login, you've got your ID and password, so you can get into the full environment, or you're in the process waiting for that email. But as soon as your environment is fully configured, we're going to want to set up all the components that we're going to use for this lab. And to do that, we're going to use a tool called Resource Manager, which is some capabilities that we have in Oracle Cloud that allows you to have a script called a Terraform script, which is essentially a sequence of commands that will start and create your networking, create images, compute images based on different shapes. So you might want to have a certain number of Oracle CPUs and a certain amount of RAM. You might want to associate a certain amount of storage, and in this case, we'll be using block storage. And there's a wealth of resources within Oracle Cloud that you can use to create any kind of application or infrastructure that you need. So these Terraform scripts that are executed through Resource Manager is what allows you to execute them, create an environment, so you don't have to go to a command line, install something. This is stuff that we've already created for you. So we're going to show you the page where you're going to kick this off from. But just keep in mind that there's a couple of steps where you first enter some information, particularly this concept of a compartment, which is where you're going to be storing all your data. And you're going to want to be using the Red Bull compartment that's created. When you click next, you'll get to a screen that shows you some information about your environment. So these are called OSIDs, which are essentially IDs for how to connect into it. And I think we've updated this interface since this screenshot was gathered. So this is going to look a little bit different. But the key thing to remember is this hands-on lab compartment. And then finally, you'll get to a screen where you'll see a little checkbox that says Run Apply. You want to make sure that that is checked. It should be checked by default, but sometimes things go a little different. You accidentally hit a space bar and deselect it, etc. Make sure that it is selected, then create. And as soon as you click create, it is going to start deploying this script. So it's going to run and start setting up everything we need for this hands-on lab. And if you want to get to see how it's progressing, we can go to the little hamburger button here, and you'll have a drop down for Resource Manager, go to Stacks, Stack Details, and you'll see your job running. And when it says succeeded, you'll know that it's all done. So everybody should click on the link. Actually, there's a missing slide here. Let me share my screen to show you where it is. So there was a link that will take you to the hands-on lab, which is this link. And I believe Tara posted it in the Slack channel. I'll move this over. So we are at this lab guide. So if you click on the lab guide, it will take you to this introduction page. And you'll see here about this workshop, and we'll have just a description of everything that we're going to do. We're going to collect some data, prepare it, load, etc. But what you want to do is, after you've gone through the steps to create your free trial, which I think everybody probably has done, and if not, come to this link. And embedded in here is my link right over here to click on. If you've gotten past that, we'll sign into your account and we'll proceed to the next lab. Now, one of the things we're going to have to do before you actually click on the link in this Resource Manager is to actually get what's called an SSH key. SSH keys, for those who are not familiar with them, are really the way that cloud security is handled. Instead of just using usernames and passwords, the SSH keys, which is a secure shell, allows you to communicate and make sure that you connect to the resources that you need. So in order to do this, you have to generate these keys. Now, the good thing is there are multiple ways you can do that. You can do it with the Oracle Cloud Shell, which is part of OCI. When you log into your tenancy, you get essentially a Linux shell that you can create your key. You can do it on a Mac. You can do it on Windows 10, as well as a bunch of other ways. So depending on what platform you're using and how you want to go about doing it, you will do it in different ways. So if I'm going to look at the Windows 10 way of doing it. Now there's a video that will show to you. So if you want to review the video while I'm talking to this, that's fine. But I'm going to use PowerShell. So we're going to come in and I'm going to run PowerShell. I'm going to run it as the administrator. And I'll say, yes, I want to do. And this creates another shell script. So if people are used to using DOS or any other shells, this will look similar. And I am now connected. So let me shrink this up a little bit. I'll keep toggling back and forth. But what we're going to want to do is issue this command, SSH keygen. So that we click on copy, paste that in. What this will do is create a public and private key. And it'll ask you, what do you want to save the key as? So here you're going to want to note that it's probably going to be on your C user ID in a directory called SSH, and then you give it a name. I'm going to call this test, just because I already have created it. I don't want to create another one. You can enter a passphrase, but basically for this exercise, just hit enter. For no passphrase, enter again, and it will create this random image, which is tied to your key. And there's other concepts like fingerprints that we're not going to cover today. If you're familiar with it or you want to investigate more, please go ahead. So what we can now do is we're going to want to confirm that I've got that script, because I'm going to need to copy it. So this will be copied into this directory. So I'm going to copy that, paste it in. I grab too much. I will do my CD, do an LS, and you see I have my ID RSA. So I probably saved my other one somewhere else. Now, the key here is when you do it, you hit the defaults, you will get it right here. You do the LS, you can see this ID RSA pub. This is what you're going to use in the next step to import. So you get that. If you're using some other things, you can actually do a cat ID RSA dot pub. You can actually see the text of that key. Sometimes when you're using clouds and keys, you might want to copy this and paste it into another text. If you're moving from Linux to the cloud, you can do that. For this, we're not going to have to. You'll just upload this file. So at this point, hopefully everybody has a key. They've got their cloud account, and we're ready to create the stack. So we'll come on to lab 1 under the introduction, which just basically says we're going to create it. And all you need to do is click on the deploy to Oracle Cloud. So I am going to click on this. And hopefully I'm still logged in. And I am not. So I'm going to log into my tenancy. I'm going to log in with my email address. And I will hopefully get my whole password correct. So this is where we get to our create stack. So you check I have reviewed. Here we see that we're going to create this in the Red Bull Hand-On Lab. I will click next. This is where you will upgrade or upload your key file. So if I come up here to see code users, Donna, and I go to my SSH directory, I would click on my ID RSA pub. So it's now uploaded, click next, and then run apply, and I would click create. I am not going to do this because I've already created my environment. So at this point, hopefully everybody has got their account, looked at, been able to connect to the lab instructions, gone through the first steps, generated an SSH key, and have now clicked on the icon in the lab here to deploy, and have gone through the steps, clicked on OK, and now you're waiting for your job to succeed. And that's kind of where we're at. This will take about 10 minutes to create. So while that's running, I'm going to go through in more detail what we're going to do with the actual predictions and the steps we're going to do to get there. All right. So let's talk about what we're going to do. We're going to build an actual predictive model to predict the top 5 places in any of the F1 races. So we're going to end up with different parameters you can enter based on the conditions or the circuit where it's racing and be able to predict it. But in order to do that, we need data. So we've already downloaded some data from a public source. The lab will give you more details of where that came from. But here we see a diagram, entity relationship diagram of everything we have. So, really at the center are the results, but we have information about qualifying times, and I'll explain the nature of F1 races in a little bit. But we have driver standings, we have constructor standings, we have constructor results, we have all the circuits or tracks, we have a list of the drivers and the teams or constructors, we have information about pit stops and lap times and all the races that exist, as well as the individual seasons. And I think there's data going back to 1950. So we're going to work with all of this data. And after we load the data, we're going to want to prepare it. We're going to want to get it ready to be used to train a model. So we're going to merge all of the data from these data sets. We're going to not use some of them. We're going to move some of the columns from others, but we're going to go through a standard data preparation step. And you'll see in the directory structure of our Jupyter notebook, we have all of these in CSV files. We're actually going to create some other things like JSON files as we go along. After we load the files, we're going to do some exploratory data analysis. Essentially, we're just going to explore the data and look at what it tells us. And this is a standard step in a model pipeline before you actually build a model. So we're going to want to compare how some of the teams are. Obviously, Red Bull is the best team out there, but we want to compare to the other top teams like Mercedes and Ferrari. We'll look at the results, the team's results, constructors, drivers, etc. After that, we'll then get into the implementation. And we're going to build a model and find the best model across a wide range of model classes. Now, this is going to be a classification problem. And some people on the call, there's people of different backgrounds. Some people may be more familiar with data science and want to understand how to apply this to Red Bull and racing. Others may, be just pure programmers, maybe have Python skills, not familiar with data science. So as I go through this, I'm going to try and balance how I talk about this based on a kind of a common area. I'm not going to go deep into Python. I'm not going to go deep into all the modeling. We'll talk about them, and you'll have your cloud tenancy to investigate however you see necessary. So we'll build all these models. And then we're going to work on serving these models to the end users. So we'll we'll look at the models, understand how they performed. Here it shows that the best one is 62%. We'll see different results and have an API REST call for the importance of it. So we're going to go through all of these steps with the ultimate goal of creating an access mechanism, an application, if you will, to predict these races. And we'll base it on this, as I mentioned, circuit, weather, and qualifying time. So pulling back up, these are the core steps we're going to do. Data collection, data preparation, explore the data, implement the models, serve them up, and have an interface to access it. Now, in order to meet those steps, we're going to use different components. Most of our work is going to be done using Jupyter Labs running Python code. Now, in the data collection step, there will be 3 separate workbooks that we have. One to collect the Formula One data, another one to connect weather data, another to collect all the qualifying data. So this is race results. After that, we'll go into another workbook to prepare and merge the data so that we can use it in building a model. We'll then look at another notebook to look at the exploratory analysis. And as you can see, we have one for modeling, for the model serving, and then actually applying, testing the models, all then to be driven here through a Python application that's using Flask and a HTML application. Now you'll notice that we have 1, 2, 3. There's 7 different IPython notebooks. This could all be placed in one notebook. And oftentimes you will do that when you're building it. We just broke them up into smaller pieces, one to make it more compartmental, but also if while you're going through things and you experiment and maybe you delete a whole bunch of things that you didn't, it's just a lot easier to recover the individual pieces. So at this point, I am hoping, if I've got my timing right, everybody should have their cloud environments, have kicked off Resource Manager, and they now have access to their environment. So, an easy way to do this is to go into your cloud environment, and you can just say, go to compute, go to your instances. This will now grab all my metadata. Make sure from here, you go to the Red Bull HOL, Red Bull Hands-on Lab compartment. And the compartments are just ways that we group related bits of services. By default, you may be at your top level, but make sure you click on Red Bull HOL and you will see that you have an instance. If you see this instance and it's running, you are ready to go. So what we're going to do is we are going to be starting up the Jupyter Lab. Now, in order to do this, you need to grab your public IP. And I will show you mine because this is not going to last. I'm going to be shutting this down afterwards. I will copy this, either Control C or Control C. This public IP address is what's going to drive all of our work. This is what's running within the Oracle Cloud. So capture your IP address, then go over to your browser, and in another window, I'm going to go to my Zoom window, erase that, press ID/8001. Oh, I forgot. Sorry, no slash. I'm thinking ahead. It's the port number for the instance, so it's :8001. And that will bring you into a little Jupyter lab, and then you're in your environment. And you can see I actually have this running in 2 separate places. So I am going to close this one because I don't want to have 2 sessions running. So at this point, we are now in the environment. So at this point, what we're now going to do is we're going to get out of PowerPoint slide world and start looking at everything that we have. So I'm going to reset my folder here, and I'll explain this in a second. All right, excuse me. All right, so I see a couple of people are still in the create stack stages. That should be finishing more. So what I'm going to do is I'm going to start moving ahead. I will go slowly. So we're just going to do some introductory stuff within Jupyter, get acquainted with the environment. If we see a big influx of people who say, hold on, we'll pause. So please let us know. But what we're looking at now is what's called a Jupyter Lab environment. So Jupyter Lab is a way to look at or control an environment for running code, saving the results, and allowing many other features that are very handy for data scientists. So I like to use it because I can run code, test it out, show the results, and keep the results there so that I can go back and look at what happened. Similar to how you would use a regular notebook where you write things down, maybe draw a diagram, it can all be in a central place. So when you get in here, there's some concepts up here. Most of this stuff is not really critical for what we're doing right now. And I'll defer on explaining some of that later. But the first thing is what's called a launcher. The launcher is the area where we can pick what kind of notebook we're going to use. And here we're using Python 3 as our language. We could add other interpreters so that we can run different versions of Python. We could create different environments of Python. So we might load certain packages. We can include R or many other items. So we can go into the notebook here and create a new one, or we can go into kind of a shell command for Python here, console. We also have the ability to use a terminal. So these are the main access points we're going to have, but you might want to create markdown files, text files, in Python. Now, all of this is essentially running on a virtual machine. So there's an operating system behind it and a file system. So that's what we see here. It's our file system, and we see we have some folders that we can sort on. I move this over. I can see we have a Red Bull Analytics hands-on lab. This is where we're going to use most of our stuff. I actually created a backup just in case I mess anything up. And we have some other programs and codes here that we're going to use later. But most of our work is going to be done here in the Red Bull Analytics hands-on lab. And when I click on here, there's some documents, there's some old stuff, there's some scripts, there's the Terraform script, a README file. In these, we're not going to use these areas, but if you look at it, we can to scripts. we can see here how we install the whole environment. If we go to old, there's a backup of all the notebooks as well. And these have a lot of the answers. So at any time, you can look at those as well. But I'm going to go into data. And then we see here's where our data is. We have data here. We have data in FR1. We have something from scratch, which allows you to do even more basic stuff. For our demo, we're going to be working on pulling data from CSV files that we've already pulled from the web. If you want to investigate how to pull them from the actual source, you can look at these notebooks later. But to start off, we're going to start looking at the first 3 notebooks that actually load data. So I'm going to double click on that notebook. I'm going to move this over. In fact, I can just click on the file browser and hide it. So I'm just looking at my notebook. So we're going to go through all the steps. And the way this will work is I'm going to talk through all the stages. I'll point out some key parts of the code. And then you on your own can either run the code yourself, and each notebook takes no more than a minute or so to run, or you can modify it and change things to meet your needs, or conversely, you can just look at it because the results are included here at all points. So this data is coming from a website called Ergas, which collects historical data about F1 racing. So it's a fabulous website that is rich in data. And we actually scraped all this that you can see the results from scratch. Let me walk through Python or through our notebook. If you're familiar with Python, some of this is going to be familiar. If you're not familiar with Python, well, I'll explain the key concepts. I suggest you just look and maybe run them. And then as you like at a later time, learn a little bit more. So first we import some warnings just to ignore little error messages. And then we're going to use this import time, start time to actually track how long this is using. So I have a matching line at the bottom. But the key thing is we're going to import this library called pandas and NumPy, which are used to manipulate the data, pull it in from spreadsheets, and create what are called data frames. And the way we do this right here is with the read command. We're saying PD, which is alias here as the package. There's a command called read_CSV, and just pull it from that data directory in a file. So when I execute that, I get, I could actually do this. You'll notice when I run a command, the line number changes. These line numbers show the order of execution. So it went from being the 4th row thing I ran to the 30th. I can then look at this and say, okay, well, there's 1,018 rows and there's 8 columns. And it's put into this object called races. And now I can look at the top of it, the first 5 rows using the function head. So now we're looking at both the head and the tail, the top and the bottom of the file, and we can see what data is in. So really, this is a very basic file telling you what season the race was, what round it was, meaning week by week. So the current seasons have, I think, 25 races, and you can see each round tells you where the circuit is, where the racetrack is located. It actually gives you the Latin long of the track, what country it's in, what date the race was executed, and we include a URL to Wikipedia for more details. So now we have an object called races where we can use for our modeling. Next, we will look at the rounds. So here we're doing, we're loading the data from races. So we're saying we're going to create an object called rounds, and then we're going to loop over each year or year, look at the races and the season, and get the unique values, and then append this list. So what we end up here, and this is looking at the first 5 objects, is by year, a list of how many rounds there are. So in 1950, there were 7 rounds. In 54, there were 9 rounds, or 9 races. So we can just get that from the file. So this is just using some simple Python code. Next, we'll look at loading races, the race results. So again, a file called race results. We see that there's 24,000 rows. There's more rows because there's drivers in each of the race. So when we look at the top and the bottom, we see here for the first race, first round in 1950 at the Silverstone racetrack. These were the drivers. We actually have their dates of birth, their nationality, their constructors, and a constructor is essentially the owner of the car, the person or the team that creates the car itself. They build the car specific for F1 racing. We see what their grid start position was, what their time, whether they're finished, how many points they received, and their place on the podium. So a key thing to keep in mind is this points and podium are very key to the standings of F1 races. Each team and each driver is assigned a certain number of points, where the first person gets, in current times, 25 points for first place. Here in 1950, you could see they got 9 points for first place. And second place got 6, third, fourth, 3, fifth, 2. I imagine sixth place was 1 point, and anyone outside of the top 6, or maybe even the top 5, gets 0 points. So as the season progresses, there's a championship for the constructors, the team that had the best results, and the drivers, and they essentially look at the number of points. But people are also concerned with the podium spots. The top 3 is where you want to end up. You want to end up on the podium, which means you finish in the top 3 spots. So here we can see the results of each race, and you guys can look through these in more detail. Next thing we want to look at is the driver standing. So we have a file that already shows the standing. Now, that could be calculated from their points, but this was already created so that for each round and driver, we have the driver points after the race, the number of wins they have after a race, their standing position. So obviously, Farina won the first race, so he's going to have 1 win. He's going to be in first. How many points he has, wins, and standing position. These, I believe, are up before. So as you scroll down, as you get to the end, you see more detail. Then we have the constructor standings. So there's driver standings and the constructors. So often teams, now all teams have 2 drivers that race in every race. So we now have, we're going to load the standings. Here there's fewer drivers than cars, constructors, so the rows are fewer. There's only 12,000 here. And again, the same type of information: season, the round, the constructor, and the metrics relevant to that constructor. So essentially, this is, if you're familiar with SQL databases, just a different group box. So after we've loaded the data, typically you want to just look at the distributions. So we use some graphing capabilities using a library called matplotlib, and we plotted for each of the features here. For my constructor standings, we could see the season and season going across the bottom, but the number of rows are. So there's actually more people in these races in looks like the 1980s and 90s than they are today. So these are how many people raced, how many rounds there were, total rounds, this constructor's points after the race. So this is an interesting distribution. Most of them are in here in the lower range up to about 70, which makes sense because except for the top teams, people are going to score points sporadically. But you can see there's some people that get into 4 or 5 and it looks like the 600s. So you can look through the results just to get an idea of what your data looks like. And then if we want to go even deeper, we can look at these constructor relationships by feature. So looking at the 1, 2, 3, 4, 5, 6, 7, 8 features by 8 rows tells you how they're related, kind of like a correlation plot. Now down the middle of these, so down the diagonal, I should say, you see the histogram. And these match very closely to what's up here. This is more blocky. This uses smooth lines. And then you can see the cross section. And I got my fonts a little small here, but this first column is the seasons and this is the round. So by each season, you can see how many rounds there are in the distribution. So you can start to see kind of where things are kind of very random, evenly distributed. Or if you look at this one, there is a very linear relationship. And this is with the constructor points after the race with the metric constructor points. Well, yeah, that in a race. So that makes sense. They would correlate. So you can use this to just get an idea of your data, and I'll leave that to y'all to investigate on your own time. So that's the basics of loading data. You use the read CSV, you look at it, you can manipulate data and put into other objects, you can review the data, and we then have the data ready to work. I'm going to expand here, and we're going to now look at the weather data. I'm going to go through this one just a little bit faster because basically we're doing the same thing with different data. But we're going to pull in our data. And again, here I'm going to want to merge races with weather. So I pulled in races again and confirm that it's 1,018 rows. I'm now going to pull in weather so we can see we have a season, the round, the circuit, and then a description of the weather, and then just 5 columns, binary columns. A 0 means it's not warm weather, a 1 means it is warm. So we can look at warm, cold, dry, wet, and whether it's cloudy out. And then we can look at our feature distribution as well. And here we're looking at the weather distribution. So here we're looking at seasons, how many, essentially this is the number of races. This is the number of rounds. What's really interesting is the weather. We can see warm weather is, looks like it's probably about 33% of the time it's warm. Cold weather is a very rare event. Dry, surprisingly, is, about 30%. Wet weather is low as well, and cloudy. So the first thing when I was looking at this is why is this? Well, it's probably because there wasn't weather data associated with some of the other older events. So if you're going to want to use weather data, you're going to want to make sure that you're using the right data. And then here we can plot the same thing we did before, looking at season. And this is because it's so binomial, it's not a very interesting graph to look at. But we loaded all the weather data. And the final loading is the qualifying data. So here we're going to load and look at what the qualifying times, the qualifying information is for all of these drivers. So here we're referring to a file called qualifying.csv. And we can see there's 14,559 qualifying rows, meaning that's how many times there was qualifying. Now, a thing that you should know about F1 racing is before they actually get to the race and they line up to start and they have an order to those, depending on where you qualify, that dictates where you start. So the goal is for a race, you want to start in the pole position. You want to be the person out front who gets a start and then everybody has to pass you. But in order to do that, you have to have the fastest qualifying lap in the qualifying time. So there's actually a couple of days of practice sessions where the drivers learn the track, get used to it. And then the qualifying goes, everybody goes around the laps for a set amount of time. And then they mark the fastest lap time that they have. And after that, in current, I think the bottom 5 people drop off after the first one. And then after the second round of qualifying, it's now 20 people drive around and they drop the next 10. And then the final qualifying round is only 10 drivers. Whoever gets the fastest time. Now, if you do watch F1, you know that they've introduced this new concept of sprint races for qualifying. We're not going to include that in here. But after we load up 1983, Kiki Rosberg for the car Williams Honda qualified with the best time of 134.526 in the first round. So you can see all there. So you can see the slow guys here for the 2019 race. You'll notice there is no Red Bull cars in the bottom. And then, like we did with the other ones, we can look at the feature distribution to understand by season, how many rows there are, by grid position, how many there are. This is quite interesting here, I found, is the number of rows by grid position from first to 25th. And you'll notice that down around 25, 26, 24, there's not that many races. Well, in current F1, there are 20 cars that qualify. So the max it could be is 20. But historically, there were races that had more cars to qualify. So that's an interesting little tidbit. We can look at the feature relationships. And the interesting thing here is, you kind of get these filled in all over the place. Well, that kind of makes sense because every race, every car is qualifying. So everything's going to kind of even out. There's always a car who's going to be in slots 1 through 20. So that's our first step of just basic loading data into our notebook environment. So I'm actually going to close these out just to unclutter my screen. And now we're going to look at preparing the data. So essentially what we're going to look at is now that we have the race, the weather, the qualifying race data, we want to join those sets together to get a more robust set of features that we can feed into our algorithms. So what we're going to do is we're just going to start merging them all together. So I'm not actually going to repeat some of the steps. In this one cell, we're just going to load all the results together. So races, results, qualifying, the driver standings, constructor standings, and weather into their own pandas data frame. So there's 6 of them. And then, of course, typically you look at them, 1018, that matches. We can look at each table. We can change the name of a column if we don't like it. So here we change grid position to just grid. So you can see that's here. Data doesn't change, just changing the column header here. We can also drop columns. So here for driver standings, we're going to drop this driver point after race. It wasn't interesting for us. We looked at the wins after race. That wasn't point standings after the race. Because we're not concerned with building a model when it is after the race. We want to know the information before the race to help predict an outcome. So those measures are just not helpful. So let's just drop them. We'll do the same thing with the constructors. We drop them. Weather, nothing to do. So we're just looking at the data. Now we need to merge them all together. So in this Jupyter Notebook cell is where we're going to merge all the data. Let me close out my file browsers, give us more room. And we can see that what we're going to do is we're going to say, we're going to create this new data frame called data frame 1. And we're going to merge command, races and weather. We're going to do an inner join, which means just a one-to-one join. And we're going to match it on the season, the round, and the circuit ID. And you notice circuit ID, these columns have to be in each of the other data frames, which is why in the prior step, renaming things to make sure they're the same is critical. And then when we merge this first one, we're also going to drop the lat, long, country, and weather column, because we're not going to need those for results. And then what we do is we just keep merging and merging. Create a new one called DF2, which is a merge of DF1, which is this line. And we're now going to merge it with results. Again, inner, season, round, circuit ID. And here we're also going to use the URL. And then we're going to drop the URL and some other columns. And then essentially we just do this with each and every file that we loaded, which is now in a data frame, until we get our final data frame. And what we can now look at is our data frame has the season round circuit, the weather information. We have drivers, we have many other columns, constructors, et cetera, et cetera. We have all these columns. In fact, we have 22 columns we can use for our model. Now, some of the things that we're going to want to do from this point is prepare the data in some interesting ways. And one of the ways might be looking at this, date. And this date is the race date. And in one of the other columns, it's probably hidden somewhere in here right after the driver, is the driver birthday. So we're going to, or date of birth, we're going to actually want to calculate their age at the race because we think it might be important, the level of experience of a driver on how well they are. So we're going to do some data preparation, some variable engineering. We're going to import this utility relative delta, which is just a function to help with date functions and manipulate dates. So we're going to create in our final data frame, our final data set, a column called date, which converts the date column to a date time. We're then going to create a date of birth column, which is just going to do the same thing, converted to a date format from date of birth. And then we'll create the driver's age, which we apply this function called relative delta, which will convert date and date of birth into years and return that as a metric. And then we'll drop date and date of birth because we don't need those anymore. We have the driver's age. So that's an example. And then I'm not going to step through each of the cells with the Python constructs, but these are common things that you need to do. You need to fill in drop nulls. So we're going to fill in any blanks with a 0. If any rows are null, we're going to drop them. We're going to convert some numbers. Remember, whether warm, whether cold, with zeros and ones to Booleans. We're going to calculate differences in qualifying times. So this is now doing some more complex mathematics to convert the qualifying times and compare them to different rounds. So we can do that. We're also going to do something for creating dummies. And by dummy columns, for many machine learning algorithms, you don't want text as the values. You want them to be numeric values, such as nationality, constructor, the circuit ID are not good as a value in a column. So what we do is we kind of flip this on the side and turn it from column or from rows in a column to an individual column for each one. So for constructor, we want Red Bull as a column. We want Williams as a column. We want Mercedes as a column. And then just for that row, if it is a Red Bull driver, we add a 1. So this function will do that. And then we could look at this and we see the whether warm, whether cold, we're converted to Booleans. If I scroll over here, we see constructor Toyota, constructor Rosso. All the constructors have their own column. And it's either a 1 or a 0 based on this season, this round, this driver, what team they're on. And that's how you kind of go about your data engineering. Now, in a typical machine learning project, this requires lots of work. There's usually lots of code here to manipulate the data. But the goal in the end is to create a data set called our F1, DF, final, CSV that has all the results that's ready to be used for a machine. So I'm going to move on to the next stage. And our next stage is around a task that's called exploratory data analysis. And you often hear people refer to it as EDA. And what EDA is really where you dive deeply into exploring your data and understanding what the data is telling you before you build your model. Now, we did some of this in the prior steps. We created histograms, we looked at some matrices to understand the data a little bit better. But this is where we really dig a little bit deeper and start doing some modeling. Now, one thing you really have to be concerned about when building a model is, has the nature of the problem changed over time, right? from some of our earlier visualizations, we saw there were races where there were more than 20 drivers in it. Well, that doesn't apply today. We also know that rules have changed. FIA, which is the governing body for F1, changes the specifications of the cars, what they have to do, how much, what the shape of it is, how high the car is. I think now it has to be less than a meter high. If it's 2 meters wide, give or take just a little bit. There are capabilities around the wings, on what they can and can't do, tires, all of this stuff around the construction of the car are governed by a very strict set of rules. And for anyone who's really interested in this, you can Google the rule books and see the specifications. I found them absolutely fascinating. But what this turns into is a set of errors of F1 racing. And we've listed the more recent ones here where, different errors were dominated by different teams because they were able to adapt to the new rules quicker and thus got ahead of the other teams and constructors on building those out. So 94 to 2009, Schumacher with Scuderia. Ferrari was kind of the leader. Then Alonso started to kind of take control, and he was with Ferrari and a couple other teams, so he moved around a little bit. 2011-13, Vettel with Red Bull Racing kind of took the lead. And 2014 to present, and I'll say present minus this year, Hamilton and Mercedes have been the clear leaders. But this year, I think Red Bull is really starting to win more, and the constructors and drivers championships are extremely close with, I think, 6 races left to go. So it's important to consider the construction of the jobs. And we're only going to consider ourselves now with data after 2010, because that's the current primary configuration of the cars. Now, interesting, after this season, things are going to change. There's more regulations that are being put in place. So the results here probably won't apply as well, or won't be as predictive for the 2022 season. All right. So with that kind of as an understanding of what we're looking at, let's get into it. Here we see we're importing the same libraries, pandas, numpy, and matplotlib. But now we're importing packages from something called scikit-learn. And we're importing a set of different models, logistic regression, random forests, etc. I'll explain those in, I believe, the next workshop in a little bit more detail. But essentially, we're just loading all these models into our workbook so that we can then start building models based on our data. Again, here we're loading data, we're merging them from where we were before, and we're doing ahead. So similar items. Here's just another useful command to list our data frame 5 columns, so we can see a list of all the columns that we're going to use. And again, we're going to do some exploratory nature. One thing I actually forgot to mention that I am going to jump back to a slide for with is kind of a hypothesis. Let me go back to my slide deck. So when you actually create a model, you want to actually have a hypothesis of what you want to predict. So I mentioned we're going to predict the top 5 winners, or the results for the top 5 of a race. But I'm kind of going to go in here with a certain hypothesis of who I think, or what features, or what's important in actually predicting that. One is it depends on the qualifying position. How well or what place did the driver qualify? It's going to depend on the team and driver and how well they've been doing in the past. It's going to depend on something I'm going to call team reliability, meaning how often did they actually finish the race? If the tires fall off, that's not good. You're not going to win a race if you don't have all 4 tires. How much does the actual racing circuit? How fast are they? How many corners are they? Does that appeal to different drivers? And also on the driver's confidence. How many times did they finish? What their points are to give them an idea of, well, Hamilton, if he's always winning, he probably feels more confident driving and would take more risk because he knows he can. Where someone who's not doing as well may be less motivated to take a risk because he doesn't want to kind of crash out and not finish. Race and tire strategy and engines are all important, but that's a much bigger problem. We're going to really focus in on these areas. The reason I jump back to that slide is because now, after we've got our data frame, I'm going to drop some of those items that are no longer valid for what I want. And I'm going to end up here with just a couple of items, their name, their surname, date of birth, nationality, that we're going to use to start building. So we've got our data frame that we started working with. Here's for those who want to read through the description, I talked about this prior, but just a quick recap. There's 3 practice sessions, then there's 3 qualifying stages. After each stage, certain number of dryers will be eliminated until just the top 10 run the final qualifying sessions. And then the race on Sunday is starts based on their qualifying position, they race, and then the constructors and the drivers get points by where they finish. The top 10 get points. Top 3 people get to enjoy the champagne on the podium and spray it all over everybody. And then all of this is important for the end of the season championship for the team. So as we mentioned, I'm going to only consider the races since 2010 due to the changes. So here we're just doing a simple filtering of the year of 2010. I'm going to rename some columns. So the name column, I'm going to call it the GP _name or Grand Prix name. Position Y is just the position, etc. I'm just going to, like nationality X is the driver national. So I'm just going to rename things. I'm going to prepare some more data. I'm going to have the driver be the 4 namespace, surname, play around with dates, get the age at the Grand Prix and day. So, again, we're doing some cleaning of the data set again. We have to do some stuff with the constructors here, something a little more. And the reason being, teams change ownership, and they might change the sponsor or vice versa. They might be the same owner, but they change sponsorship. So here you can see we want to make everything say Aston Martin if in a prior year it was called Force India Racing Point. And that's because at some point there was a big scandal and the owner of the team had to give up ownership. But Aston Martin still retained, so when they did that, some people still, they bought the team, it's the same drivers, the same cars, but they got a new sponsorship. And we wanted to keep that all together. And the same thing for Alpine, was Lotus and Renault before, Toro Rosso became Alpine. So this happens fairly consistently. And then we do some cleaning up in our data because at some point it was called BRI for Britain instead of the UK. America was abbreviated AME, etc. So we go through our cleansing. Now we want to get into the did not finish or DNF specification. And we want to calculate when a driver didn't finish as a flag and when a constructor didn't finish, meaning did the driver crash the car and that's why they didn't finish? Or was there a mechanical problem with the constructor, right? The engine blew, or a hose, an oil hose blew and they couldn't repair it. Because we want to kind of assign blame to either the driver or the constructor. And basically what this is doing is looking at the status ID, which has a list of all the conditions of why a driver didn't fail, and say if it's any of these codes, assign it to the driver and assign the value 1. If it's any of these, give it to the constructor. So we'll do that. And now we've got a data set we can start looking at. And this is kind of like our final exploratory work. So we could look at the DNF that did not finishes due to driver error. And we could see this wonderful driver Lucy, 21.6% of the races, he did not finish the race due to his error. I suspect his career was not very long. And you can see that decreases down to right around here. We can, let's see, Valtteri Bottas doesn't have, he's 4.2, so he doesn't crash a lot. Champions Vettel and Hamilton, they're still very low. And you'll see more champions here. They still crash due to their fault. They're not perfect, but you'll tend to see the better drivers here compared to down here. With, you might make an exception for Michael Schumacher, who seems to have crashed a lot, but he's won a lot of races. So maybe he was just in the camp of, I'm going to go right on the edge, and I'm either going to win or not finish. And then we can go look at the same kind of analysis for the constructors. So the interesting thing here, and remember this is the last since 2010, Red Bull, Ferrari, Mercedes, the teams that win the most have the least amount of time that the car fails. The teams that are down here are not on the circuit anymore. So I'm not going to go through each and every one. I will leave it to everybody to go look through this, because what we're doing here is really we're just assigning points and we're looking at them by drivers just to get a feel for, does this hypothesis, that DNFs and confidence makes sense based on how they're driving. Look at their driver's podium finish percentage at their home race. So you can see, Lewis Hamilton at his home race finishes on the podium 69.23% of the time. So does that influence their confidence? Do they get points? Red Bull at their home track gets points, meaning, top 10 in 85% of the races. So I'll let you guys just kind of look through all of this data on your own, because we've explained all that before. It's all cleaning up data for 2021 as well and repeating it. And then we just have a couple of checkpoints to validate data. And then we're done with just the final EDA of our data. Okay, so just to recap, we've loaded data, we've engineered it, we've changed it, we've modified it, we've filtered it, we've fixed nulls and zeros and all this other stuff. And we believe we've got where we want to go to start building a model. So let's do that. So what I'm first going to do is kind of go through a little bit of explanation of the different types of models we're going to use, the different algorithms we're going to use for classification. And I'll admit this is going to be a big challenge for me to get this done efficiently, because I tend to like to talk about it. But we're going to use 6 algorithms. The first one is called a logistic regression algorithm. And this is basically a statistical technique for doing these kind of classification problems, where essentially you have a logistic function, which is a probabilistic method that assigns, what the probability is along this curve. And essentially you say, you'll score things and you'll give it a probability. And if it's above 0.5, well, or a certain amount about 0.5, it's more likely to be this classification, a win. If it's below it, it's more likely to be a 0. So this is a very tried and true methodology that works. Sometimes it creates the best outcomes, sometimes it doesn't. The next thing we're going to pass through is called a decision tree. And a decision tree is essentially a set of rules that has these decision nodes that you start off based on some criteria. So as an example, the model might say that, if the age of the driver is greater than 27, then finding the most likely outcome falls down this path. If it's less than that age, go down here to a subtree. And then down here it might say, okay, well, if the weather is rainy, then go to this sleep node. If it's not rainy, go here. So essentially it's saying if a driver is under 27 and it's rainy, this is the most likely outcome. This might be win. Otherwise, it's a lose. So decision trees can be very wide with lots of different breakouts. They can be very deep with different rules. But essentially, you have this tree methodology which gets you to the right answer. Now, these aren't super precise. They work well in some areas, but they don't work all the time. So there's this new concept, it's not new, but a newer concept called random forests, which attempts to take what's called an ensemble of decision trees. It uses the basic functions of what I just described with a decision tree and go down different paths. So in essence, it might say, instead of 27 being the first thing we look at, maybe that's the third thing, or maybe it's not 27, maybe it's 30. And they create all these multiple different trees. And then at the very end, the algorithm figures out how to bring them all together to give you a more optimized route. And it all depends on the characteristics of your data. So in essence, a decision tree is here and left and right node. A random forest has multiple trees in it. The next one is what's called a support vector machine. And essentially, this is what's called a supervised learning method that allows you to be very effective in what's called high dimensional spaces, meaning lots of variables. It's also interesting and effective when the number of dimensions, so there's say 100 variables, but you only have 50 rows of data. Typically, that doesn't work very well in a lot of machine learning algorithms. Support vector machines support that well. So there's several different mechanisms on how to do these, but essentially, it's a way to classify it, creating the best fit on what's called a hyperplane. I think I have an image down below that helps show this. Gaussian naive Bayes is just another methodology, which is really based on naive Bayes and probabilities. So you have class probabilities, the probabilities of each class in the training data set, what actually exists. So we know that Lewis Hamilton wins 50% of the races. We know that rainy weather is 10%, et cetera. So you have that information, and then you use conditional probabilities to mix this all together to get distributions to identify the likelihood of anything else. And then the last one we're going to talk about are called K nearest neighbor algorithms, often referred to as KNN algorithms. And essentially what this does is it plots all the points, and here we're looking at essentially a two-dimensional representation. It can be used with multiple dimensions. But it basically says, okay, if I've got a series of points here, how can I split them up so that they're all closest together? So all these, I'll call them green, dots are all grouped together. So those get classified one way. All the yellow ones get classified as category B. And then when you enter a new data point, the algorithm will say, okay, is this new data point closer in a kind of a coordinate system to this group or this group? And here it says, well, it's a little closer here, so I'm going to assign it in this category. So that's a very quick high-level overview of the key algorithms. And then the next thing is, feature importance. We want to understand which of the features. We're going to be using several ones like PNF and weather, et cetera. Which one are most important in predicting who's going to win? And then you can go and visualize the data. And there's several different visualizations that you'll use. Scatter plots, histograms we saw before, box plots are very useful. Heat maps are useful, but you're going to want to use this to look at the model, understand how well it's doing, and make sure you get the right data or the right model. So that's an overview of modeling. It's kind of, a couple hours of machine learning explanations into probably 5 or 6 minutes. So let's actually build this model. So the first thing with any building a model, you want to split the data into subsets called, multiple data sets. And this is very common. It's standard best practice. In fact, it's actually the essence of doing machine learning training, where first you take a data set, like we have our large data set, and we're going to create a training set. This is a percentage of the data set, maybe 70, 80% of the rows, usually randomly selected, that you use to train your model. This is what we're going to run through all the algorithms to figure out a model, to actually train and create a model. But after we do that, we don't know if the model is right. So this is where we're going to then test that model on a subset of that data, whatever's not in the training. And see, does it actually do a good job predicting the data? If it doesn't predict anything, then our model's not really good and we'll have to redo it. There's also another third set for validating data that uses to really optimize models after you get it. We're not going to use that. Depends on the problem whether you want to use it, but training and testing is always used. So you split it up, you then start building your model. You decide on your training method. Essentially what models do we want to see? We want to check for accuracy and bias and all these things you think about that we've already done here. But then you train the model, as I described, and you're looking for the best fit of the model. And as you look at a lot of the machine learning libraries in Python, you'll often see something like this that says model.fit, where fit is the function to test it or to do the fitting, and model is the definition of the model, which will specify, do I want to use random forests or support vectors, etc. And then you assign your data, you send in your data as an array of values, usually labeled X, and what you're trying to predict, which is usually defined as Y or labeled as Y. After you train it, there's this concept of model fitting. You'll hear this all the time of, is a model overfit or is it underfit? And essentially what this comes down to is if you train a model, say on the full data set, and you create that model explicitly, so it matches every value because you tweak it and say, well, if this row is, the driver is 27 and it's rainy and they started in 5th place and their constructor was Red Bull, then I know they're going to finish in 5th place. Well, that's very overfit, right? It doesn't account for lots of other variables. So you want to create something that's a little more general than that to help predict. And the other side is the underfitting, as if you kind of don't have enough information and the model is not very accurate at matching the data. So that's the last thing just on general machine learning building that we do. So let's build a model. Here again, like we saw before, we import lots of metrics or lots of or models. We see the random forest, the support vector machine, decision tree. We also import some other items that are going to help us build this model. We're going to load in our filtered data from the prior data set, and we're going to do a head. And we'll notice that we have about 4,800 rows of data. So we're almost ready to build our model. What we're next going to do is we're going to create those confidence metrics. And essentially what we're going to do for this is we're going to create the confidence metric for a driver based on did they finish the race divided by the total number of races entered. And then we'll subtract that from 1 to give us a definition. So we can see what their confidence level is. And we're just using this as a metric to say, if you finish the race, you're confident. If you didn't, you're less confident. So you can see a lot of these are in the 90%, but there's some down below here. Lance Stroll is 87%. Michael Schumacher here is, or Mick Schumacher is 1. Interestingly, Michael Schumacher was point low. So you can see this isn't a perfect representation, but it's good. We're going to do the same thing for instructors, looking at their success metrics. And Red Bull is 83%, Mercedes 88%. Some of these others are much lower. Alpine right now is 53%, which is really not very good if you're only finishing half the races. So we create this confidence value. We look at only the active constructors, because now we're looking at predicting just 2021. So we only want the 10 current constructors, the 20 different drivers, and then we create our data set. And as we look across, we can see the year, the date, their position for the races, all the way down here, and we have their confidence levels for these, as well as whether they're an active driver. All right, so prepare the data. We're going to actually store this model so we can deploy our user interface in this directory. So we create the directory called models. We're actually going to create one more metric called position index, which basically says if it's less than 4, if the position is less than 4, return 1. And less than 4 means they're on the podium. If it's greater than 10, meaning they get points, return a 3. Otherwise, it's 2. So very, top 3 is 1, 4 through 10 is 2, and 3 is 1. We then say, okay, let's get going. We're going to create a X variable, a data set that has just our X variables. And these are the ones we're going to include: the Grand Prix name, position, driver, age, position that they finished, driver confidence, and active drivers. We're only going to include if they're active. We're going to then do a little more fitting to transform like the Grand Prix name and the driver. So instead of it's their name, we're creating that grid of 0s and 1s for each driver and each Grand Prix. We create our Y value, which is the position they finished, because we want to be able to predict the position. So this is where we're training. And this XY is what we're going to build our model on. So this is our final data set. So here we'll come in and we'll say, these are our models. We're going to use logistic regression, a decision tree, a random forest, SVC, Gaussian, k-nearest neighbor. We're going to create a dictionary that has the models and the names for descriptive purposes. We just create blank data frames. And then what we do is we loop over each of these models. So each of these models, and we use this thing called k-folding, which basically says, take a data set and randomly split it into different little buckets and then train on those. So it's a way to take a data set that might not have thousands or hundreds of thousands of rows and just do multiple simulations of training. Here, we're going to get the result of this training by saying we're going to run this algorithm controller called cross-val score. We're going to pass it in the model. And since we're looping over the models, it's going to do it once for each one. Here's where we say, here's the features, the X variables. Here's our Y variable, which is the position. We're going to use our CV that we described. And we're going to score this based on accuracy. We're going to use a basic measuring trick to say, just how accurate does this model work in predicting the data? Now, there's other metrics that you can use, like an R2 score, there's F scores, there's other things, but we're going to use that. And then we're going to add all of the results into these variables and then print them out. So now when we print them, we can see logistic regression classified at 93%. decision tree was 91.7, random forest. So we can look through all of these and decide which one is the best model. Now we can look at the numbers, but we can also look at them using a box plot. So we can see here, the random forest has the highest mean. Also, there's a pretty good variation. This one has less outliers, so it's much tighter. So this is where you can decide on, are you going for the best overall mean, or do you want something a little more consistent? Clearly, the Gaussian doesn't perform as well. So that's the model for the drivers. And then we do the exact same thing for the constructors. I'm not going to go through the code here, but we end up with a model, and we see here that it looks like the support vector classifier actually performs a little bit better. So this is where you never know going in what the best model is going to be for a specific problem. So that's actually, we now have our models. We do have another section here where you can create a model based on drivers and constructors. So this is where you're going to join them both together, build a model. Due to the amount of time that we have associated, you're not going to have time to do this right now, but you can, you have your cloud account, lots of credits. If you're inclined, go test it out. In their directory, under the docs directory, not the docs, I'm sorry. Where is it, the results? We already have the finished examples here. Let's go over here. There's the model and solution. So you can look at that later. But at this point, we are really close to being done. We've built our models. So the last part is deploying it or model serving. So what we're going to do here is we are going to go through and look at our data. So here we've got our DNF stuff. So it's, at this point, it's kind of showing the same stuff again. So it's kind of a notebook, a self-contained notebook. So a lot of this is duplicated. So we can go through and go through this. We'll get down to the models. So here, what we want to do is we want to generate a qualifying data set for the actual predictor. So this is a data set that we're going to actually predict. So here we're just going through and doing some other data preparation to get the race, the driver, qualifying position. We get their last race information. We're now going to say, let's build the final random forest, because we looked at the prior step, we looked at all of them, but let's actually build it and deploy it based on this random forest, which is why this code is really just copied from the other item. So I'll just kind of go down. We see the X-train and X test. We run the classifier through this. We fit everything on the training and the test. And the key thing here is this cell. What we're doing is we're now saving this model and all the weights of the model, all the things that go into the code that we created, into a pickle file. And this pickle file is going to be used for the user interface that we're going to look at to predict our items. So when you kind of just click on all the code, it will actually create this file. And you'll see you can actually look at it in the models.random classifier pickle format. And this pickle format is a Python compressed format. Think of it almost like a zip file, just with more stuff in it because it has logic of the information. And then we see, we look at what the random forest feature points. So we mentioned we only have 6 different features that are used for this model. But we want to actually look and see which features are most important. Meaning, Is their confidence the most important? Is the constructor the most important? So this part up here, create the model, create the pickle file, we're now just going to import it again. So we're going to load the model back into our notebook session. We're going to look at the importance, and then I'm just going to do some basic control features to then print out the plots of each importance. So what this chart is telling us is for each of the features, the Grand Prix name, the position, the constructor, the driver, etc., the qualifying position, here about 75%, is the most important feature in predicting who's going to win. Simply meaning where they qualify is the biggest predictor of who's going to win the race. The next two biggest are the driver confidence and the constructor reliability. Those are the next most important pieces. So you can almost go in and say with 75% confidence, that whoever qualifies first is going to win or has the best chance to win. Second and third, et cetera. If you're in 20th, you're going to need some miracles. And then what we can do is we can plot the decision tree. We can look at this high level, and it's a big tree, but each color here represents one of the different metrics. Or I should say variables. And it starts off here, and it goes, well, depending on the condition, I'm not sure what the blue one was, it would go down to the left, all the way down until it gets, what it thinks the outcome it expects. So this is the decision tree that gets created. If we plotted another decision tree, say we just redid everything, we can get different formats. So remember, we've had different estimators. This is just plotting a different decision tree that can be created. And essentially what we can do with because the random forest has multiple decision trees, what we do here is we look at all. So remember, the colored boxes represent a different feature, the constructor, the Grand Prix name, the position. And you can see, depending on these estimators, they look a little differently. And that's how a random forest kind of figures out all these estimators, then pulls them all back together to give your final estimate. So I'm going to take a drink of water. Voice is listening, but we're going to now, that's essentially, we built the model, we looked at how it performed, looking at ultimately how it decides who to win, but let's look at the final result. So the good thing is we've already created an application for you to create this. But in order to kick it off, we're actually running this in a little web server. So we're going to need to get to the terminal. So there's an easy way to do this. You can go File, New, Terminal, and it'll open up a terminal here that will paste things in. The other thing is, if you remember from our launcher, you can click on this link here for the terminal. It'll put you in the same spot regardless, but that's how you get there. So all we need to do is cut and paste these codes. I'm actually going to grab all three of them because I think I can paste them in. And basically what we do is we're changing to the right directory where the web server is. We're going to source and activate an environment that has this, and then we're just running this code to run the scoring, running Python, and there's this app.py. We're not actually going to code this in the exercise, but you can go in, look at this app.py code, and run it. So the last thing we have to do is just call this HTTP colon 8080. So I need to grab my public IP address. I'm just going to copy it from up here. I'll copy it right. Open up a new tab, do colon 8080, and we get our application. So from here, what we can do is I can say, well, I want to see who's going to win the Circuit of America And let's assume it's going to be a dry day. Now, when I click on predict, it's actually going to call that model that we put in the pickle file. And it's going to pass in these values and actually predict. And what we'll see is something very distant. It's going to predict that the podium, Lewis, Hamilton, first, Max Verstappen second, and Valtteri Bottas as the top three on the podium. And then the others, Lando Norris and Sergio Perez, will be the next two. So you can run this, you can play around with different circuits, different weather patterns, and predict and see how the results change. Based on this season, Lewis and Max are dominating the victory platform, or the victory spot, #1 spot. So most models are going to have them winning. So you're not going to see too much variation. I have seen the bottom three vary a little bit more. But that's essentially the end of going through all of the model building. So I took you through loading data, preparing the data, doing exploratory data analysis. We then built some models, we evaluated those models, and then we actually deployed them to an application that you can use. Now, if you're going to do this on your own for any problem that you have, you're going to get, the process is going to be the same, but the code and the steps and maybe the models you have will vary based on the specific thing that you're working on. So with that, I hope everybody enjoyed this. I'm going to turn it over to Tara for a couple of concluding remarks. To drink a whole bunch of water, but I do thank you all for attending. Feel free to contact me at any point if you have questions, you want to dig deeper, or you want to see how Oracle can help your organization apply machine learning in the Oracle Cloud. So with that, Tara, I'm going to switch over to the presentation and give you back control.
Great, thanks, Brian, for the fantastic presentation. So we do have some additional resources here that we'd like to share with you. If you enjoyed today's session, we'd like to invite you to our next session on October 21st, and that will be learning about how to deploy apps and microservices with Verrazano and Oracle. And then the next link is where you can stay tuned for our upcoming Red Bull Racing Honda hands-on labs. And then we also encourage you to share with us any feedback you have on today's session or what you'd like to hear from us going forward. So we have an email that you can reach us at, as well as a survey there. So let me just go ahead and drop those in the chat now. On our next slide, we'd like to test your knowledge on what you learned today. So if you take this quiz and complete a few questions correctly, you'll achieve a social badge, which you can share on your social media. And then our final slide, we wanted to let you know that Oracle University is now offering free access to OCI training, as well as free certification exams through December 31st of this year. So be sure to check out that link to get started with your learning. So with that, if there's no more questions, thank you again, Brian, and everyone else for your help. And thank you all for spending your time here with us today. The recording of the workshop will be available on the Masterclass event page and sent to you via email as well within the next couple of days. So thanks again, everyone, for joining us here today. We hope you have a great rest of your day and to see you again next time.
Thank you very much. Bye-bye.